Hey, this is Matt Baxter. The following video is for a class project. The goal of the class is to learn computational methods for solving differential equations, and then to apply these methods to problems in electrical engineering. The problem I chose for this project is the issue of crosstalk between IC interconnect. This occurs because ICs are fabricated on such a small scale that wires in close proximity exhibit capacitance. This capacitance allows signals to be transmitted between wires erroneously. To understand this behavior, I set up a model that produces a pair of coupled PDEs and then solve these PDEs under various conditions. I developed this model from the distributed RC line model already discussed in class. Here, a segment of interconnect has some resistance and capacitance per unit length. By repeating these delta x segments and taking the limit as their length goes to 0, we get the following equation, which takes the form of the diffusion equation. So how do we account for coupling capacitance? We might have a situation like this, where two lines of interconnect run parallel to each other. Because this geometry is symmetric along the length of both wires, we can add a new parameter, coupling capacitance per unit length, C sub C. By taking two segments of the distributed RC line model and linking them together with our new parameter, C sub C, we get a model capable of describing crosstalk. Now there are a few assumptions we made here. Namely, the two wires are identical. For a more general model, R and C for each wire could be different. To get the equations from this model, we solve KCL and KVL for a segment of both wires. Then we take the limit as the segment length goes to 0, as with the distributed RC line. And this is what we get. Here the equations are in terms of the second partial derivative of position. Since I'd like to use a finite difference approximation in terms of time, first I need to solve for the partial derivatives of time. Doing so results in the following equations. In these equations, d1 and d2 represent constants in terms of r, c, and c sub c. Now we can implement a forward difference in time and a central difference in space to solve these PDEs numerically. Notice here that v beta is always in terms of a half time step. This is to leapfrog, so to speak, as the solution is being computed between the two wires. Also notice that delta x here has a different meaning. Now we will not be taking the limit as delta x approaches 0. Instead, delta t and delta x are parameters that determine how precise the solution could be. Now that the method of solving the system is developed, let's take a look at what we can find out using MATLAB. For the first demonstration, wires will be initially uncharged, and then only one wire will be driven to a logic high value with a finite rise time. Here we can see the driven wire pulling up a voltage on the undriven wire. If the coupling is strong enough, this could cause transient errors in the undriven wire. The circle represents when a driven wire reaches 4 volts, an arbitrarily chosen threshold for a logic high value. This simulation showed a capacitive coupling equal to the normal capacitance. In this case, the threshold is crossed at about 31 time units. Now we will see what happens when the capacitive coupling is 0, and the normal capacitance is twice its previous value. Notice here that since there is no coupling between the wires, the undriven line remains at 0. Here again the threshold is crossed at 31 time units. This can be described as effective capacitance. When one wire is transitioning and the other is steady, the effective capacitance is the sum of C and C sub C. When both are transitioning in the same direction, the effective capacitance is simply C. When both are transitioning in opposite directions, the effective capacitance is C plus 2 times C sub C. The next simulation will show opposite transitions. Here the coupling capacitance and the normal capacitance are set to the same value of 2. we can see here it takes about 46 time units to cross the threshold. What will happen if the normal capacitance is set to 6 and C sub C is set to 0? Again, it takes 46 time units to cross the threshold, which follows the effective capacitance rule for opposite transitions. Now consider the following. Instead of wires being parallel, what if wires cross perpendicularly? In this case, only a portion of the wire will be capacitively coupled. For the sake of demonstration, let's let C sub C equal 10. Here, the crossover will occur at the driving end of both wires. Here, the effects of coupling are minimal. The delay in the driven line was hardly increased, and only a small voltage was seen on the undriven line. Now let's see what happens when the crossover is set near the load ends of both lines. In this case, the coupling occurs between position 8 and 10. The driven line takes much longer to reach the threshold, and the transient voltage on the undriven line is larger and lasts longer. So what's going on here? When the crossover was near the driving end, the voltage could easily be dissipated by the undriven line. When the crossover was near the load end, the voltage had to dissipate through the entire length of the undriven line to reach ground. This lingering voltage increased the effective capacitance for the driven line, making it take longer to reach the threshold. Well, that's all I have. Although this was more of a qualitative look at the issue of crosstalk, it can easily be adapted to a quantitative analysis by using real-world parameters. Thanks for watching.